Hello, everyone. I'll be presenting an abstract for preparing spectroscopic tools for the future space missions and utilizing Raman spectral mapping and eventually scanning electron microscopy and infrared multimodal analyses to characterize lunar and asteroid simulants. So simulants play a critical role in the planning and execution of measurements on bodies such as the moon, Mars, and asteroids. Because they remain primary targets for upcoming manned and unmanned missions, a comprehensive understanding of their characteristics is vital. Understanding this provides context for data that will be collected in situ. Researchers can anticipate the ranges of materials that they may encounter, and it helps the development of algorithms for onboard instrumentation and data processing. Raman scattering happens when a beam of monochromatic laser light interacts with a molecule. Most light scatters elastically so that scattered photons have the same energy, frequency, and therefore wavelength as their incident photons. However, a small portion of that light is scattered inelastically. This results in photons with energies of different wavelengths than the incident light. When this happens, it transitions between different energy states, and this Raman shift in wavelength is characteristic of specific vibrational transitions in the molecule, and hence it's unique to the compound that's being studied. By measuring the Raman shifts and their intensities, one can identify compounds present in the sample and their relative abundances as well. Portable Raman spectrometers have expanded the application of this technique to fields as diverse as material sciences, pharmaceuticals, environmental science, and as well as geology. So why Raman spectroscopy? Raman provides detailed information about a wide range of materials in making it useful for spacecraft missions, where IR is sensitive to polar bonds and heteronuclear group vibrations such as OH stretching in water. Raman is sensitive to homonuclear molecular bonds and vibrational modes such as CC, single, double, and triple bond. Raman spectroscopy is a mostly non-destructive method, and that's crucial when dealing with samples where it's critical to preserve as much of the original material as possible. And also, unlike methods such as IR, which might require extensive sample preparation, it can be performed on rough, unprepared surfaces, making it great for in situ analyses. Advances have made it practical for space exploration, such as the fact that they continue to shrink over time and have already been incorporated into rovers and landers for direct and remote characterization of material up to 1 kilometer away. So in total, we plan to analyze the compositional distributions of 7 unique simulants. These simulants were procured from the class Exolith lab at the University of Central Florida. Several other forms of simulants are also available from their website, but pictured here are the Lunar LHS-1 simulant in the center, along with some of its properties, as well as pictures from top to bottom of the CI, CM, CR Asteroid, and LMS-1 lunar simulants that we also have. Here, I've provided a table of our 7 samples, as well as some of the characteristics that are found in the fact sheets that are provided, as well as a list of parameters that we plan to investigate in total. So far, we've taken both individual spot spectra and spectral maps of 3 of the 7 samples in most of the available parameter space. As we could see from the previous tables, that asteroid simulants are mostly magnesium serpentine, olivine, pyroxene, magnetite, with coal substituting the PAHs, and the lunar simulants are principally anorthosite, pyroxene, glass-rich basalt, and mixed in with ilmenite and olivine. During the preliminary phases of analyzing the samples, we adjust the parameters to maximize the signal features while minimizing our noise. And choice of magnification depends upon the individual grain sizes for each of these simulants, since we want to make sure that our measurements identify changes in the mineralogy over large enough spatial distances. Laser wavelength and power are also determined by the level of fluorescence that's seen, as well as detector saturation. Once we have a better understanding of which parameters allow for the best spectra, we continue by taking several maps, each with at least 25 individual spectra each, for an optimal set of laser wavelength, magnification, and power settings that are found. As stated previously, Raman is good for analyzing minerals as well as organics, and there are databases for many known minerals, such as the RUF, which allow you to include or exclude minerals of interest from the main material that you're looking at. And Raman and IR are complementary to one another, but Raman spectra are highly dependent on the instrument condition, where the parameters that are chosen will change the resultant features significantly. We minimize the level of difference between these maps and the individual spectra by calibrating for each sample with laser wavelength and objective magnification used. Our sample is loaded into a copper sample cup that you see here. It's tapped on the table to distribute the sample throughout without compressing it, and then a razor blade is used to clean off the excess over the lip of the cup. From here, we analyze the sample, and when done, we return the remaining sample, and the sample cup is cleaned with acetone. As far as our spectroscopic analyses, data is exported in a text format and is used to generate spectral maps for defined limits of interest, in this case within a range from 50 to 3,000 inverse centimeters. Each spectrum undergoes asymmetric least squares or ALS baseline correction, and this automatic process intends to retain feature visibility while enhancing the uniformity of shapes between each point spectra. Next, we employ find peaks from the SciPy package in order to do automatic peak detection and setting a threshold to exclude irrelevant noise or insignificant features. Then peaks are fitted again, aiming to minimize the discrepancy between the sum of the detected peaks and their baseline subtracted curve. When the best fit is found, graphs of their peaks, their centers, and their sum are shown, as well as the SNR of the data itself. The maps are taken to try and strike a balance between the efficiency per map and the spectral feature fidelity. And the balance is influenced by acquisition time, number of accumulations, data points per map, and other features like the laser wavelength, which affects the Raman intensity that's seen. For the preliminary results, we have a few spectral maps for our carbonaceous simulants, one of which is shown here on the bottom right. This spectral heat map was taken on a CI simulant with similar settings as the measurements shown above it in black and red. The pair of plots seen above are various versions of my peak fitting Python code described earlier. The fit code has improved with the older code that's shown here on the top left. Since I've only been able to update this within the last couple of weeks, I'm hoping to try and use this with some of the better data that we have, such as the blue curve that's seen on the bottom left. Adding more points to these maps and increasing the acquisition times for individual points have the biggest effects on the time that's taken per each map, which is why spectra that comprises maps like the bottom right usually have data that looks kind of like the data in the top left due to the time that we're allowed on the instrument at a time. This blue curve at the bottom took 20 minutes on its own. So what will we show using IR and SEM in combination with this? Well, we intend to use a nearest neighbor analysis sometime in the future to characterize the clustering of points that are most similar with characteristics or features that align with others around them. And understanding this homogeneity of the sample at different objectives is important, as this is where the multimodal approach will be used. We also want to know at what scales do the characteristics tend to change and what sample volumes give similar or different results in between. With our FTIR instrument that we have in our lab, we plan to take complementary IR spectra and process for atmospheric and water interactions that occur in the mid-IR. And as for the SEM, we plan to use the Zeiss SEM instrument that we have on campus to provide extremely high quality images of the surface structure of these samples. So just to talk a little bit about that new equipment that we also have beyond this, we have acquired a new nano IR instrument with an OPO laser and a confocal Raman TERS with 532 excitation, thanks to an NSF MRI award, as well as we're setting up a picosecond Raman instrument facilitated by a separate Picasso grant. This instrument is planned to take remote very rapid detailed images of 750 by 750 pixel images with up to a fifth of a micron in resolution in only 45 minutes, procuring up to 500,000 spectra at a time. And we aim to leverage this collected data and the results to hopefully enhance the accuracy of measurements conducted using Raman for spectrometers, enhanced hopefully by the nano-IR photothermal instruments, with a particular emphasis on the spatial distribution of Simulant's compounds. This approach will not only refine future measurements, but also make data expectations more reliable for upcoming missions, therefore benefiting experiments performed by landers and rovers in the future. This understanding of Simulant's compositions aligns with NASA's planetary exploration objectives, especially regarding chemical differentiation and characterizing interstellar objects. And we plan to try and extend this study to new Simulants with a number of Martian ones at our disposal. So with that, thank you all for listening.